Hey, good evening, everyone. Oh, there it is.
Hello.
Hi there. It's me. Okay, some people need to be let in, and others not. Right? It's quite interesting. I don't really know what the difference is, but so far nobody waiting. Okay. So how can you hear me? Can you hear me? Okay.
Hey,
Okay.
I have a question about the written exam.
Yes.
Do you know if we have to have a letter of recommendation to write it?
Um. What I have done in the past, I've sent out a certificate to each of you saying you attended X hours of ground school. So you should. Oh, somebody wants to come in. Sorry. So I have to see how I worded this, and that should do in the past. This has done, but I'll find out. Good question. Thank you.
Okay, thank you.
Okay, so I see Noah. Hi, Noah. Thanks for submitting all the homework. Good stuff. And Brad, thank you very much for sending out the videos. So you must have found a way to upload it to YouTube. Yeah, it's. Let me just plug this in. Can you still hear me? Is it better now or not so good? Now, it's it lower. So quieter. Okay. What about the voice quality? Is it better or worse? Okay. So if you turn up your volume a little bit, you should be able to hear me then. Hey, thank you. Okay. Then I'll keep the I'll keep the headset on. Okay. So we're still waiting for a few people. So who had fun with the Magellan question? Who could figure it out? Nobody. Hey. Hi, Greg. How are you?
Good. Sorry.
Okay. Can you hear me well? Good stuff. And
I think I figured out the Magellan question, but I'm not sure if I'm right.
well, tell us if you
Well,
want.
if you're traveling west, you're moving towards the setting sun. So your day, you eventually lose that day. You lose it, yeah. Where if you're traveling east, you're traveling towards the rising sun.
Yep.
So you gain, you're catching up on the day. So each day is shorter and you gain the day.
Yep. That's. Does anybody have any other explanation? But you're right on. So you're a sailor, right, Ray?
Yeah.
And yeah, he basically Magellan sailed around the world against the direction of how the globe turns. The globe basically turns west to east. If you would stand on the equator, right, and if you look east, then you're looking more or less into the wind, right, the way it's turning. So he was circumnavigating the globe the other way around, and this way he lost one revolution, basically. But it's exactly what you're saying. Every day was just a little longer, and therefore he there was in the end there was one day lost. Okay, Greg, we don't hear you.
No, that's good. My brain's catching up to you guys.
Okay, very good.
My brain's a little tired. I never made it home last night.
Okay. Yeah.
Just working
Yeah.
in the office.
Hmm. So we are still missing. We're still missing a few people. Right? We're missing Doug.
I'm just gonna go run the bathroom real quickly. I'll be right back. Okay.
Yep. Yep. Yeah. Absolutely. And we are missing Reg. So well, we are 5 minutes into it, so we should get started as soon as Greg is back. Yes. Why is this when you sail around the world today? Like Ray, if you would, I'm sure. Have you ever had any plans for circumnavigation?
No, I don't think so. I'm not a really big sailor, right?
Ah, yeah. I was when I was younger. It was basically one of it was in my life as a plan, but then I decided it takes too much time. I better use the time for flying.
I've
And
read quite a few books about sailing around the world.
yeah, yeah, me
They're
too.
quite interesting,
So the people who do this today, they don't have this problem, right? Why is that? They don't,
Well, they know the date lines.
right. They sail across the international date line, and with that, they advance a day.
Yeah.
And
So,
they click the calendar one forward, right? And this
and
is
of course, that didn't exist in Magellan's time.
that's right. Yeah, he didn't have that. So I will give you another riddle for at the end of this session, or I'll send it to you. That has to do with the international date line. I'll see who figures that one out. Okay. And thank you very much for doing your homework. There were also a few things I wanted to revisit from the last session we had there. So what we want to do today is yeah, who found the high point on their chart? Hands up. Everybody hands up. Okay, Ray found it. Yeah. Nobody else? Guys, ladies.
My eyes couldn't tell the difference between all of the colors. I was looking for so long. I couldn't find the highest point.
Ah, so you didn't read my clue.
I was looking for I looked at the colors,
Mm-hmm.
and I don't know if I just didn't see orange or there is no orange, but
Okay. Well, I'll explain this in a second. Let's ask Greg. Greg, did you find the highest point on your map? You are muted.
Sorry, never made it home. I didn't have a chance to sleep last night. I had to work.
Oh man, really? Yeah, yeah, yeah.
Yeah.
That sounds bad, you know.
Um,
Yeah, I
one
think
of those nights.
a doctor would tell you you need more sleep. You need your sleep, right?
But first, I want to thank Brad for all those recordings. Brad, you're wonderful.
He's our hero. Really well, really good. Thanks, Brad.
Yeah. Because one of the things I just wanted to say is that it's taking, I need a lot of repetition. I need to go back and forth to look at these things, and that's been very, very helpful. So thank you.
Okay.
The way my brain's working right now is that I need to pause, reflect,
Super.
go back. So thank you.
Okay, and we have Doug. Hi, Doug. Can you hear
Hi,
me?
sorry, my browser wasn't letting me in. I was up there as a D for a little while, but okay, sorry about that.
Yeah, yeah, yeah. I had problems with starting the Google thing today as well, right? That's why I was a little late too. Okay, so we were just talking about finding the high point on the map, and Ray found it. And Doug, did you find the high point on your map?
I thought it was over in the Adirondacks.
Right.
Uh,
Okay. How did you?
how did I find it?
Yeah.
I was coloring a bit, and then I saw the contour lines, and then I realized the Adirondacks were there, so I figured that must be.
Okay. Well, let me bring something up and share that with you. And there's an easier way of finding this. Just stay with me there for a while. I have we need a JPEG. Okay, this one. the other one? This one. Okay. And oh yeah, I should actually turn on the recording. Sorry for that. We'll do that too. Just hanging on there. Also, I guess, Brad, you're recording again, right? Brad, are you recording again? Okay. Well, then we don't have to bother with this. The Google recording is really not good because it doesn't give any, whatever you say doesn't show, doesn't come through. So we won't record. We will rely on you, Brad. Thank you. And we'll share a screen. And we'll share the entire screen here. Share, and it gives me a warning about things, and it's coming through. Okay, we make it a little bigger. So this is the legend, the back part of the legend of your chart, right? So when you come in, and some of you looked at this, right? You see the tinting here, and obviously this is the highest point here. And it says here the highest elevation on the chart is located at this at those coordinates. That's how you find it. I see some people laughing. Yeah, so it is really easy, right? But yeah,
I looked at the coloring, but I didn't notice the writing right above it.
yeah. So, but it is in the Adirondacks. When I looked at this, I was thinking, there's no way there's something 4600 in Ontario, right? But the map also covers part of the US, and it covers the Adirondacks, and it's there. And there's even contour lines there. So okay, and the other interesting thing is the contour line interval is 500 feet, like from one line to the next, at below 4,000, and on this particular map, and then it's 1,000 spaced 1,000 feet above 4,000. So I mean, it doesn't really, it only goes to 46, but the maps out west where the mountains go to 12,000 or 14,000, there this kind of stuff is important, and you could end up with a map that covers the Rockies, the Canadian Rockies. That's why we're bringing this up. The other thing on the map I wanted to quickly share with you, and also correct the mistake I made the last time we talked, is, okay, so let's share this first. Okay, so there is in the class F airspace, the C by A's, where the A is the advisory, right? Remember that? And then there's a number, because every airspace is listed in a book. And then there's another letter behind it, and that letter is telling you what's happening in this airspace, right? A stands for aerobatic, right? And H for hang gliding, S for soaring, T for training, and so on. And you may get asked, well, what is the symbol, right? I mean, if the symbol is this, you know what it is. It's a glider. What is this, right? And don't get stifled, because it won't say ultralight beside it, right? It just shows you that symbol in a class F zone. It's an ultralight. And so don't go, oh my God, I've never seen that. But what's that supposed to be, right? Everything else is pretty self-explanatory: hang gliding, parachuting, power flying, and training. So I wanted to do that. And then last time when we talked about the Alberta airspace there, and I will just put this away and put this away too. Nope. Yep. And we go to Sky Vector. Okay, can we have, okay, it's filling in.
and we have to. Oh, okay. Remember, we looked at this airspace, and we were wondering what this is because this could be a question. What is this? And we thought this is the mode C whale, whale like the bridal whale, right? Now, no, it is when it's sort of a ragged line like this or a jagged line, then it is always a change in the floor of the controlled airspace. It doesn't say which it is here, but it's definitely a change in the floor. It's going lower down for the approach into this airport here. And the reason why we got this wrong is bring the map up again. Yeah, this here, we just zoom in on it. The reason why we got this wrong, we looked at we looked at the legend here. We saw this is the line, right? And it says mode C right above it. And that's why we got it wrong. The mode C is actually is a line that is a smooth line like this. This is the mode C whale. And they call it a whale because it is not a different airspace. It just says within this line, you need to have a mode C transponder. Sometimes there's an altitude associated with it, like in southwestern Ontario near Toronto. You need to have a transponder at above 6,500 if you're a power plane. Now, gliders are still exempt from transponder requirements, but we all have transponders, just to be on the safe side. But so gliders at the current, the way the regulations are currently, gliders don't need a transponder at all. But of course, they won't let you into Class C airspace, and they call it and the mode C transponder thing is basically the airspace boundaries look like that too. But if there says mode C, then within this line is a mode C transponder is required, and we have that in on the Ontario map. That was pretty much there was one of the lines that were close to Tilsonburg. Remember there our map exercise. There was a line that was the mode C line. Let's see if I can pull this up for a moment. No, I don't have it open, but we can open it.
So gliders can't go into this airspace without the appropriate mode C transponder. Is that right?
No,
Or
no.
not?
First of all, no. Gliders can fly. So this here is the mode C line. This thing there. Can you see my cursor? It should show up. So this is a circle that goes around Toronto, and so the Toronto airspace starts further in. I cannot move the map. This is just a segment of the map. But this line here is not an airspace line. It is basically where from here on you need to have a mode C transponder in your power plane. In your glider, you don't because gliders are exempt of transponders. Now, if you want to fly into Class C airspace, which is, for example, the Toronto Class C that's further in, give you another map, and it shows that. This one. Yep. This is the this is the this is the one. See this ring here? This This is the transponder. Sometimes they call it a whale, or and if you look at it, it says here transponder mode C required above 6500. So inside is this side here, closer to Toronto. Power planes need the transponder mode C above 6500. The Class E airspace, it looks on the map, it looks the same as the transponder line, it's maybe a little thicker. This is all these lines, right? And this is the Toronto Class C airspace. And as you know, if you want to fly, you can fly VFR in Class C airspace, but you need a clearance. And as a glider, if you want to fly into the Toronto zone there, without a transponder, they say stay out of this. Go away, go away. We can't have you here. So you cannot really fly into that Class C airspace without a transponder. Even if you have a transponder, it is questionable if they let you in because gliders do not fly straight and level. Gliders always descend a little bit, right? And the whole traffic systems, how they control the traffic is they assign a certain level to every airplane, so they can't hit. Now, they have a real problem with an airplane that cannot hold an altitude like a glider. That sort of goes down, down, down all the time, and then finds a thermal and goes back up. Right? This is a controller's nightmare, and therefore that's unlikely that they would that they would let you in. A few years ago, when only one SOSA member had a transponder in his glider, Alan Daniel, and he was flying back there somewhere, right? And he was coming back here, and he called up Toronto, and they were super accommodating. They basically let him fly right through the airspace here, coming back to SOSA. But this was because it was a novelty for them to see a glider and hear a glider that even had a transponder. Nowadays, every glider, or all our SOSA gliders have transponders. So if we start calling up Toronto, they say, go away, go away. We can't deal with you because it is difficult for them. And it's the same, of course. The Kitchener control zone is also a Class C control zone. So they will, with a transponder, they will let you fly through because you're not in there long. Like it's basically a 5 mile radius, so 10 miles, 18 kilometers, you're through. And if, for example, you're up there where this glider is, and zoom in a little bit. Let's say you're up there where this glider is, and you want to go to SOSA down here. You call them up; they will likely. Hopefully, you're probably high enough to fly over it anyway, but you may dip in. If you're not high enough, then you won't make it. They will probably let you through the Class C airspace. I was in that situation a couple of years ago before I had a transponder in my glider. Jersey had one, so they let Jersey go through, and I asked if I could fly through too, and they said, "Do you have a transponder?" And I said, "No." That no, you can't go through. So I had to basically made a lot more work for them by flying all around there. Anyways, any other questions to um, maps? Oh yeah, and I made a mistake the last time we were talking. I was talking about the Class E floor. I was talking about 500 feet. This is wrong. It's always 700 feet. So the Class E floor, there's no lower floor than 700. And so this is, again, this jagged line here. This is where the airspace, the Class E airspace steps down from 2200, which is and this is 22 AGL above ground to 700 above ground. 22 is pretty much the norm because this is the lowest airways can be above the terrain. 22, and that's why the 2200. Okay.
When are these above sea level and when are they above ground level?
Most is above sea level, but the Class E the Class E floors, they're above ground because they're so low, and they depend on where the ground. They follow the ground basically, right? And so those are above ground. all the Class E levels. But for example, if you go, and I have a better map here, um, all the the ceilings and the floors of the Toronto airspace. This is all above sea level. So this outer ring, the ceiling for that one, where we cannot go higher, is 3,500, and it's 4,500 in this wedge, and then it drops down to 2,500 here in the inner ring, and it goes down, down, down. This is all MSL. The Kitchener control zone. The control zones quite often have both AGL and MSL because their standard control zone is standard 3,000 above ground AGL, right? So the Kitchener one, they rounded it up and they said, well, it's 4,000 MSL, which is easier because if a plane flies along and the altimeter is set to sea level, then he would have to figure out how much is 3,000 above ground, right? It's not so easy to figure this out because he doesn't know. I mean, he can get the elevation of Kitchener and then he can add the 1,000 feet, but or subtract the 1,000 feet. But it's much easier if you just read your altimeter, right? So the 4,000 here is above sea level, but somewhere it also says probably 3,000 AGL or so. I don't think it's the 2,500 here, it's something else. Okay, and then I wanted to show you something else on the map. I think I have this already open. Let's have a look. This guy here. So when you take a closer look at the Toronto class, this is the Toronto Class C north of Toronto. Again, the inverted wedding cake. And this is the VNC, the Toronto Terminal Chart, the VTA, which is 250,000. So this is what's inside the box that's shown around Toronto. Remember this box? I don't have this open anymore. And what you see here, it shows you on this ring here, and in this ring, it shows you below 700 AGL. It says AGL here, right? Below 7 AGL. This is uncontrolled airspace. Above 7 AGL, it becomes airspace E. You don't need to contact anybody in airspace in Class E airspace. But above 2,500, this is basically where this Class C starts. It's Class C airspace, and you need to talk to Toronto Terminal. And this goes all the way up to 12,500. So this is how to interpret this. And then the next outer ring here, then it says above 3,500. And remember, I just said the outer ring is the floor or the ceiling for us. For us, the ceiling is 3,500. So this is where the airspace starts at 3,500. And this is means MSL. And it's Class C airspace. And they give you again the frequency, and it goes to 12,500. And above that, it'll be Class B or Class A airspace anyways. Probably Class B. And then Class B, VFR flying is already pretty restricted. You need lots of equipment, not good for gliders. So, but we are in Ontario, we don't fly that high anyways. Okay, any questions to the charts? And oh yeah, and then there was something else. Remember when we or you tried to figure out how do we figure out the heading when we were flying from Sosa to Tilsonburg, how do we get to the heading? And I explained, well, you have to measure the angle between your true course line or your true heading and one of those meridians, right? So this here is let me see. This here, there's a meridian here, so basically a longitudinal line. This here. And okay, so this line goes through that red spot, which is the 0 on my triangle there. And if I line, and this is my true heading line. This is what I've sort of marked in the chart. This is where I want to go. Now this nice triangle, because it is actually for exactly that purpose. I bought this, I don't know, probably 40 years ago. It's quite nice. It shows two directions. It shows something about 55, right, or 54 in a little bit. That's when you go this way. This is your true heading. Remember, this is north 0, 54, then east, then you're flying east is 90, and so on, right? If you fly this way, there is, see this, 240, 250, 230. So basically this 230 and about 235. So this way 235, this way 45, 55, sorry. Now, whatever triangle or protractor you have probably doesn't have this luxury that you can read it both ways. So you have to basically figure out, first of all, in what quadrant is my heading. Like, is it in the first quadrant is 0 to 90, the next one is 90 to 180, the third is 180 to 270, and the fourth is 270 to the 360. You have to figure out, let's say it's in the third quadrant, so it's got to be, and then you have to add and subtract until you get to that to a number that's in that quadrant. So depending on what angle you're measuring, and you should always be measuring an angle to one of the meridians, to a longitudinal line, right? And but if you measure, okay, this is 55, and you want to go southwest, it cannot be 55, right? So add 180, and then see, and then this is how you come up with your 235. All good? Understood? It's awfully quiet. Any you want me to explain this again? Because there may be something like this, I don't know, in the exam. Yeah, that's perfect. Yeah. Okay, that's good. And VIP, that's basically a mail order service, right? And how long did it take to get to you? Oh, okay. Yeah. Yeah, I mean, though, if it's something for flying, it probably goes both ways. And if you want to spend the money, it's the only time you will ever need it. You can order it from VIP Pilot. I'll put it's a website. I'll, the website is, I think, vippilot.com or so, right? So, but I can look it up and put the website in the next email. You can also buy it, I'm sure, at the Kitchener Airport at the Flying Club or something like that, and get it from there. Okay. Any other questions to charts? I guess we beat that to death. Okay. So oh, and the other question is, it comes up a couple times, and is always, and people get this frequently wrong, and that is the rumb line. So there is a typical question: what, there is a line where you cross every meridian at the same angle. What is this? Is it a great circle or is it a rumb line? And that is a rumb line. So let's revisit rumb lines and great circles. Okay, do we still know what a great circle is?
supposed to be the shortest distance by a circle.
Yeah. And there we are. And it's the shortest distance between 2 points on the globe. They are always on a great circle. But what is really a great circle is it, and this is here the description. A great circle is basically a circle that where the center is in the center of the Earth, and the peripheries around the globe. That's a great circle. Always goes through there's 3 points, right? It has the 1 point, the other point, and the third point is the center of the Earth. That's how a great circle is. It's basically you cut the orange right in the middle, then the two halves show you the great circle of the orange. Okay, and then the projection what we are looking at is that between the 2 points is of course on the surface. That would be something like this, right? Sort of that this goes from India to New York City or so. Now, depending on the map projection you have, this is the good old Mercator projection where all the meridians are parallel and they never meet. Which means in the north it is really distorted, right? Because there's the North Pole is spread out over the width of the map. So the great circles definitely look anything but a straight line, right? Look at this. And if you would make a straight line from San Francisco to Bangalore, that would be a rhomb line because it would cross every meridian at the same angle. That's the definition of the rhomb line. And the great circle is way different. Now, our map projections are not like this. For the maps we use, they're more like this, where they're sort of a conical projection. Oops, I'll leave this here. We can actually start this up, then it's a little clearer. Okay. So, for example, on this particular map, the globe is better approximated, and you see all the lines of longitude. They all sort of they converge on the North Pole about here. So there, a great circle isn't all that far off from. It looks much closer to a direct line, right? And interesting, the next one basically compares the two. So this down here is the Mercator, see nice and squares again, and well, not squares, they're rectangles, but all the meridians are parallel. They don't meet at the pole, whereby on this here, the orthographic projection, but they also call it a conical projection. Again, the meridians, they converge to the pole, and a rhomb line on this kind of map would already be not a straight line anymore, right? If you just want to cross every meridian at the same angle, since the angle here is different than the angle there, it becomes a sort of a bent line. And the great circle line is pretty close to a straight curve line. Not quite, but it comes pretty close, right? Whereby this projection here, the Mercator, the rhomb line is straight because it's a Mercator projection, and you cross every meridian at the same line, at the same angle. And the great circle, what you really should fly, is more of a curve. So the upshot of this is there's great circle, it's the shortest distance between 2 points on Earth, and there's the rhomb lines. This is basically a straight line that crosses all meridians at the same angle. And if you put a line down with a ruler on your map, that's pretty much comes pretty close to a rhomb line, right? And the way they used to fly these great circles is basically they made a sequence of rhomb lines. Basically, they made short ones and they approximated the circle that way. Nowadays, of course, with GPS and computers and so on, the computer knows all this, right? So nobody has to plot anything anymore. And the other interesting thing is that the rump line will, if you keep on going on it, will actually in the end up on the North Pole in the Northern Hemisphere and on the South Pole in the Southern Hemisphere. Simply by crossing, you see the angle beta here, always the same, and that basically makes it sort of spiral up to the North Pole. Okay, but on a map, this would certainly be a straight line between 2 points. And if the points are really far apart, then it's much better to go on short distances. It doesn't matter, but if it's a longer distance, in a longer distance, for example, going from the East Coast to the West Coast, you save quite a bit of distance by following the Great Circle line, not a rump line. Okay, are we all rump lined out? Any more questions to this? So there's a typical questions, and we have come across those. Well, there's a straight line on a map, this projection, Mercator projection, or so. What is this? A great circle or a rump line or whatever, or a straight line between 2 points? What is this? And you can easily lose a point unnecessarily by getting that wrong. Okay. Any other questions to this so far? Then yeah, how did you do with the weather homework, the cloud heights and all that kind of stuff? Who did it? Be honest. Ah, Jimmy? Jimmy, you're so perfect.
I looked at it, but I didn't do the whole test. I have to be
Okay.
honest. Been busy this week.
Yeah, no, it's fine. Let's go through that. And there was basically a lot of weather information, and then there were some questions with that, right? And I've got to find what questions there were. So stop sharing here for a moment. Okay. Sorry about that. Okay, we got it now. So this was the weather information here. Remember that? I'll set this apart here and then I open it again. Mhm. Okay, there it comes. Jesus. I think my computer is struggling here a little bit. There's too many open windows. Okay. Question number one. Can you see that? Make it a little bigger here. Does it show up? Yeah. Okay. Question number one. What are 4 likely clouds you may observe to help detect a warm front and place them in the proper order, commencing at the highest height? Okay, do we remember what the clouds are when a warm front comes through? We at the time we decided, or we learned, these are all layered clouds because the warm air runs up and over top of the um, cold air, and therefore these are sort of layered clouds that are running up. Okay, so we'll start. What is the highest layered cloud we have?
That
Anybody?
would be the cirrus.
That's the cirrus. Okay, and what is the mid-level clouds? What are they called?
Stratus, isn't it?
They have an alto, like the mid-level. Stratus can also be a lower cloud. The stratus can be a high cloud, then it's a cirrostratus. It can be an altostratus, so a mid-level cloud, and then it can be a nimbostratus. This is a low-level, rainy, layered cloud. So it's not a convective cloud. It is basically just a layer and it rains out of terrible weather. Okay, so what answers do we have here? We have cirrus, cirrocumulus, altocumulus, and altostratus. Is this the right answer?
What is the ACC? I didn't on the chart. There's no ACC.
It's altocumulus castellanus, I would say, something like that. But the A says alto, and that means mid-level, right? So yeah, so we're going from the high level to this is also high level, and then we go mid-level, and then we go still mid-level, right? Altostratus. So it's not really coming all the way down. We're going from high level to mid-level. Okay, let's look at the next one. This is cirrocumulus. These are basically little dotted cirruses. Altocumulus, altostratus, nimbostratus. So yeah, this goes from high level to mid level to low level. That's possible. And then we have cirrus, cirrostratus, altostratus, nimbostratus. Definitely, this is your typical warm front thing. You first have a cirrus, then it thickens and becomes a cirrostratus. So this is where you have sort of a milky sky, but you can still see the sun sort of a little bit shining through. And then it thickens more and it gets lower as the altostratus, and then you get the nimbostratus where it's raining. So that is definitely with a warm front that would be it, right? And then the last one is cirrus, cirrostratus, cirrocumulus, altostratus. We're not going down. Right? We're not getting to the lower layer. So this is nice. Highest layer, thicker layer, middle layer, low layer, low level layer, nimbostratus and rain. So this would be the right answer. Okay. So in Canada, which of the following would most likely produce the highest chance of freezing rain? Do we know how freezing rain is happening? Freezing rain is yeah.
It's a when the air is warmer up above, it starts out as rain. It comes down through a freezing level and flash freezes. No, I'm wrong. It super cools, and then when it hits the ground, it flash freezes.
That's right. So super cool means the raindrops are below zero, but they don't have a core. They need something to trigger the freezing, right? And if it's not there, the super cool means they're cooler than freezing, but they haven't frozen yet. But as soon as they impact on something, they freeze right immediately, right? And freezing rain can occur on the ground, and it's pretty nasty because we have everything gets covered in ice. If you're old enough, you remember the huge freezing rain we had in '98 or so. Was the worst in the Montreal area. I mean, Montreal was out of power, I think, for 4 weeks or so, 3 weeks, because the huge power towers, the electric towers, they collapsed under the load of the ice. There was so much ice on everything. It was amazing, and all the forests, they lost all their limbs, and only the trees, the vertical trees, were still standing. It was I remember in '99 I was driving up to Montreal. I was driving through that area where it was really bad, and it was an amazing sight to look at the forests. That was the freezing rain on the ground. So that happens when there's a warm front in winter, let's say in January, and there's a cold area that is where it's maybe around just a little below zero, not too much, maybe -1 or so. And above, a warm front comes in, it's above zero or above freezing higher up, and it starts raining out of a nimbostratus cloud. And just as Doug said, the drops fall through, and then they fall through the cold air layer that is still on the ground. And by the time they hit the ground, they're super cooled, and bang, they immediately freeze. But where it's even more heinous is if you experience this in flight. And in flight, it is basically if there is super cooled airdrops around in a cloud, and you fly through there with your airplane, you turn into a popsicle really quickly. And it's called clear ice. And clear ice is the worst icing because it is massive, and pretty soon the airplane will be so heavy that they can't fly anymore because it's just too heavy to fly. And also the airfoil will be covered in ice, and it will not be a proper airfoil anymore. So it's also losing the lift, and the windshields will be covered, crusted in ice. You can't see anything anymore, and this is extremely dangerous. Fortunately, for gliders, this rarely happens where we fly. However, last year, when we had our New Year's flying, well, New Year's meet at SOSA, we usually meet at SOSA New Year's Day, and when the weather is good, we fly. So the weather was okay, so we took a couple gliders out and launched the first one in the air. However, the clouds were a little lower than we thought, and at 400 feet, the glider disappeared in the clouds. The glider released, and they came down and landed. And in that short time, it had a crust of ice on it, just a little bit, but it affected already the handling of the glider. We thought, this is not good. Let's try one more. The second one was even worse. We decided we gave up. We said, no, this is way too dangerous to fly. But if you're flying along with a power plane and you're flying, let's say, at 10,000 feet, slightly below the freezing level, slightly above the freezing level, so it's below 0 Celsius, and you encounter some liquid precipitation that freezes at the airplane. It's bad, 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 bad. You have to do something immediately, otherwise you crash. And as I said, fortunately, usually not a problem for us. We had a bit of icing when we towed a glider a few years ago to Brantford for early season checkouts. And the Sosa runway was too soft, so we did this in Brantford. And on the way over, the ASK 21, Rafael Bravo was flying it, started to ice up. And he had to actually release and land. And it became the first off-field landing in the year, the season. But otherwise, these are the only two occurrences I know where it was a problem with the gliding. Okay. So okay. Okay, so let's look at the question. In Canada, which of the following would most likely produce the highest chance of freezing rain? A warm front in late August? No, because it is not below 0 in late August on the ground. A steep lapse rate? No, there's nothing to do with the lapse rate. This is just to throw you off. C, behind a cold front in late August? No, because it's not in the cold front, it's in the warm front, remember? So D, ahead of an advancing warm front. It doesn't say what time of the year, but it's typically in the winter. If you have a warm front in the winter, you get two things. You can get freezing rain, and you can also get fog. Why would we get fog? Does anybody know that? We get fog. Yeah.
The warm air is saturated with water, and as it comes over the cold air can't absorb. The dew points meet, and you get the fog.
Yeah, almost correct. So the warm air is usually pretty humid, and when the warm front is such that the warm air is coming down to the ground, so let's say warm air is flowing over a field that's snow covered, then the field is so cold and it starts cooling down the air close to the ground, then you get fog there right away. And it's quite often when it's January and all of a sudden it starts warming up because a warm front is coming through. Expect fog. Be careful when you drive. Okay, so let's go. What is a squall line? Any takers on that one? Jimmy knows, eh?
So that would be I think it's a narrow band of active thunderstorms, so C.
Yep, it's a narrow band. It's called a line because it's a band, and it can be pretty active thunderstorms. So would if it says here it's a buildup of nimbostratus cloud formed in a line, can this be?
A nimbostratus would be, just a big system. It wouldn't be a short line.
Yeah, nimbostratus would be nice, gentle rain, right? Not very violent in any ways, and so on. So This is would not form thunderstorms. There's two. There's two different types of clouds. There's, as I said, the layered clouds, and then there's the vertical clouds, and there are also convective clouds. So if we have convection, this is when all these cumulus clouds go up. And we like those when they're small because this is exactly convection. This is what gives us the lift in gliding. And if the convection is really strong, remember when we showed you all the clouds of the cumulonimbus and so, that's a convective cloud. And uh, a squall line always has CBs, like cumulonimbus clouds, in it that makes the squall line. Thunderstorms, basically. So what do we have? So it's definitely not A. We have B, cloud development resulting from an inversion. No. Um, Cloud development doesn't result from an inversion. Um, a narrow band of active thunderstorms that are non-frontal. That's exactly what it is. It's not a front going through. It's just a squall line, but it forms a line. So yep, that's the one. And then there's another one, Altocumulus castellanos. In the mid level, they're cumulus, but they're not really convective cumulus. They look like a cumulus cloud, but they're not. They may be a little bit convective, but not strong, right? So it is the narrow band of active thunderstorms is a squall line, and they can be quite vicious. So the airplanes better be put away when that arrives. Okay. Um, I don't think this was on the list of questions, but we can look at it anyways. What is a cyclogenesis or genesis or whatever? I'm not really sure how to pronounce that. Any ideas?
I'll take a crack at it. I just cyclogenesis. I'd say the creation of a lower cyclone.
Yes, that's exactly what it is. It's so whenever there's also a frontal genesis as well. Whenever you see sort of the suffix being a genesis, that means it's the beginning. It starts. And cyclogenesis, the cyclone is a low pressure area. And the cyclogenesis is the starting of a low pressure area. So it's not a psychedelic rock band, not the development of a high pressure system, because a cyclone is always a low pressure system. It's the creation of a low or cyclone, and that's what it is. And the breakup of fronts and systems, they have also a suffix that's something like lysis or so, like frontalysis. That means the front's dissipating. Um, I haven't seen that on a cyclone or so, but at some point the stuff dissipates. But whenever you see the Genesis word, it means it's the beginning of something, right? And it's the beginning of what it says up front. It could be a front, or it could be a cyclone, or whatever. Okay. Okay. 5 types of fog. That's something we touch on the next time we meet. All the various types of fog. We haven't really talked about this, right? See what we have for fog here. There's radiation fog. Radiation fog is when overnight, when you have a clear night in May, say, so the air is still fairly cool, and it's clear, and the earth is radiating out all the heat, or a lot of the ground is radiating out the heat it picked up during the day because the sun was pretty good, and it gets really cold. And then we have the same thing again we had with snow covered, where the front sort of, or where warm air goes over snow covered area. The ground is cold, and the layers close to the ground will then form a fog. It's usually pretty shallow fog, but it can be pretty dense nevertheless. That's radiation fog. Upslope fog is when air mass is driven up a slope by the wind, is basically the forming of clouds, and where it's pushed against the slope, it appears when you're standing on the slope, you have, because you're now standing in the cloud, you have fog. Okay, frontal Arctic. I don't know. I have to look this up. The Arctic sea smoke, what that is. Haze isn't really fog. So okay, but I'll look this up and then we'll talk about the various areas of the various types of fog there are. Okay. Which type of fog may form when there are these four criteria: high pressure system, light winds, high relative humidity, and condensation nuclei. That means there's in the air there's little particles where the water can condensate around. Right. This is just like with the ice. If there's no particle where the water can change from gas to liquid, then fog cannot form. But if particles come in, all of a sudden, boom, fog forms. And the water can change from gas to liquid, and the next changes to solid when it freezes, and it needs a nucleus for that as well.
That's why London, England was so foggy
Yeah,
years ago because of the coal heating.
yeah,
There was
because
so much.
they had so much dirt in the air, right? It just loved the fog, just loved that, right? And okay, so what kind of fog would under these conditions would we see? Any guesses?
I would say radiation.
Yeah, it's a typical radiation thing, particularly if there is if there's light, if there's not much wind, right? And so it sits there, the air gets colder, right? It's in a high pressure system. That means the sky is probably clear, right? And it's cooling at night, right? This is where you get radiation fog. But let me see if I can find a picture of that fog. I can show you. Okay.
I read years ago in London at Heathrow when the fog was really bad and jet fuel was cheap. They parked two 707s or two Comets at the end of the runway and blow towards each other and clear the threshold at least.
Yeah. That would, I mean, it warms it up, right? And that would certainly work, right? So where is my?
It would add a little bit more smoke though in those days.
Yeah. No, my fog photo, unfortunately, is not in there. I should put it in there, but it's not in there. Oh, no, there it is. There it is. Okay. So that's your typical that's your typical sort of radiation fog. Early in the morning, you see the sun's already up, and it goes. The terrain is sloping down. There's a river down there, so there's the sort of cold air sitting in this puddle, and this is where it forms the fog. That's so typical, and it's in fall, right when the nights get cold, because you can see the colors there. So probably October, and this is where you get the foggy mornings. That's the typical radiation fog, and it will clear out. I mean, as the sun warms up the ground, it'll disappear. But early in the morning, when you have to go to work early, there could be patches, particularly when the road sort of slopes down into sort of a little valley or so. Watch out, there could be fog sitting there.
If you camp in the fall, a lot of times you wake up to fog, wet picnic tables, everything's soaking wet in the morning, and it burns off pretty quick. But
Yeah, your tent's all wet. Yeah, I don't sleep in tents anymore, but I used to. Okay, I'll come back to our. Okay, then. So this one is something that comes up pretty soon or pretty often. It's the lines that join equals of something, right? So what lines join equal pressure on the surface of a weather map? What are they called?
Isobars?
They are the isobars, yeah. Any lines with equal stuff are always iso, and the lines of pressure they're bars, right? So isobars. So it's isobars, and then the other question is um, how far they're spaced. It says here alternate, but the question is how far are they spaced apart? Remember that? They're spaced every 4 millibars. So that every line, an isobar is a line with a certain millibar number attached to it, and they're spaced out 4 millibars. So if we look at that, let's take a look at this. So this is the American prog chart. Okay, there we are. You see the high here. This is 2 highs. So it's a high pressure ridge. And the high is in the center, it's 1033. Can you see that? I'll make it a little bigger. Okay. Now we lost it.
Yeah, we could see it on the last. Yeah, we can see
okay.
that.
There it is. And then there's an isobar around this, and this is the 1032 millibar isobar. So there's none further in because the 1036 doesn't exist. The high is only 1033. And then there's the next one is out here. This should then be the 1028. So I have to go out a little bit. Yep, see, this is the 1028 here, the next one. So 4 millibar spacing. And do we know what, if they're really close together, what this indicates? Everybody knows that, right?
A lot of wind.
Yeah, high wind, because the closer they are together, the more of a pressure gradient you have, and that's driving the wind. And so if you look at this map here, this is actually today at 7 o'clock, so pretty much accurate right now. So we have a little bit of snow here, so we are here. There's no really high winds anywhere. The isobars are pretty far spaced, right? So not much going on. There's a bit of a low out here. So it's a pretty calm situation. It's it's sort of the Arctic air mass, and not much happening there. Sometimes there's a really big high up there up north, but it doesn't show that. It's just sort of. So when they talk about the polar vortex, we are pretty much in the Arctic air right now, and quite often there's pretty high pressure, but that doesn't mean it doesn't snow. And right now we have a weak low, right? It's 1015 millibars, not very strong, and sort of a cold front going through. That means it will get a little colder again shortly. Not a big change. It's just a very weak. And see this thing here. So that's a front that is sort of dissipating. That would be a frontolysis or lysis or whatever. So if you ever see that, okay. Let's go back to our question.
So just a question about flying. So it's you'll fly better in a high pressure area.
Yeah.
Is that how come we don't fly in the winter very much? Because the runway problem, is that the reason?
Well, number one, and we do fly in the winter sometimes, but number one, the we cannot fly if there's so much snow that we cannot move the airplanes
Yeah.
on the ground anymore, right? So then sometimes the hangar doors are frozen shut and stuff like that. The other thing is, yes, it's high pressure, but the sun is so weak that it cannot generate thermals. Back when we fly sort of in February or so, when the sun gets stronger, the ground is still cold. And particularly when the snow cover breaks up, so there's then green or black areas or green areas and still snowy areas. There can be pretty good thermals then. But a closed full snow cover like right now just reflects the solar energy, reflects everything back, so it does not warm up the ground. And remember, thermals need warm ground, so the ground warms the air, and the air then climbs up. And we fly in summer in highs because it's sunny weather. Even though in a high, the air mass, general air mass actually goes down. Right? That's why we have the sunny weather. But it sinks at about 0.2 knots. So the question would be, well, how can you fly up? How can you climb when the air mass goes down, right? The air mass has a general weak sink, 0.2 knots. But within that air mass, we have bubbling and convection and so, and thermals with 3, 4, 5, 6 knots, right? So they overcome that overall descending of the air mass. In a low, the air mass actually goes up. The air flows into the low, right, and the air mass goes up. But that's why we have bad weather, because it forms clouds. So it would be much better for gliding, but the clouds cut off the sunlight, and then we have bad weather and rain, so we can't fly there. That's why we fly in high pressure situations. And
Yeah.
ideally, we like to fly behind cold fronts because then the air is nice and crisp and very convective. So when you read my weather reports, I always write about convective air masses and all that kind of stuff.
I read something about a thermal index. Do we ever use that very much at all?
Yes, that's sort of the thermal index in some of the, for example, the SkySight and so. And it's basically a question how the steeper the lapse rate, like the faster the atmosphere cools with altitude, the better the thermal. So high lapse rate means more convective activity. A very low lapse rate is not good for thermals, because if the air mass that goes up cools down, and then pretty much it will be cooler than the atmosphere, the surrounding atmosphere, and it stops. Because the atmosphere, a low lapse rate means it does not cool much as you go up. A high lapse rate means it cools very quickly as you go higher. And that keeps the thermals going. And all this is in the tephigram. So there, the tephigram is basically a thermal picture over height, over altitude. And you can read a lot of things out of a tephigram. Okay, so let's go back. Where are we? Okay, so question 7 here. Isobars, 4 millibars. That's the right answer. Isotax, there is no such thing as an isotac. And 6 millibars is wrong. Contour lines. Remember, that's another thing. What's a contour line? Do we know that? That's a line of equal height.
That's the height of the land.
Yeah, that's the line. These are the lines that are on your chart, showing that the grade and the terrain. These are contour lines, so they don't have the ISO name, even though it's also a line of equal height. It's also an ISO something. Okay, and this is also wrong. So okay, let's look at the. Okay, so now we are looking at. This is, by the way, Toronto here. We're looking at the upper wind forecast. So we have another one here. So here are the forecasts. And this is the upper wind forecast for Toronto. 3,000, 6,000, 9,000, 12,000, and 18,000. And the question is, what is the forecast wind direction at Toronto at 6,000 feet? Okay, so we look at it. 6,000 feet. Toronto. I see 2521 plus 12. What does that mean?
So that's 250 degrees, 12 knots, and plus 12 degrees above standard.
Almost. It's 250 degrees, 21 knots.
What did I say?
12 knots. Yeah, you misspoke, right? So it's 200. The first two digits. That's the direction, and you have to add a zero there, and and then the second two digits is the knots, the wind in knots, and those is the temperature. So it has plus 12 degrees, 21 knots, 250. Well, what's so 230 is wrong. 250 is okay. The question is it true or magnetic? It is actually true. The wind directions, even in the TAF, are is always a true north direction. So not magnetic. I don't understand. It's an en route wind direction. True is fine, but I don't understand why they do it in the TAF, because you really want the runways are lined up with magnetic north, right? The runway number. So if you land on runway 36, it's 360 degrees magnetic. And so if you have a wind from 360 degrees in the forecast, it's not magnetic, it's true. So you have an angle actually. And the angle is basically the variation. So it's not big. I mean, it's 10 degrees in where we are.
And what about the METAR? That must be true, is it? Because you're taking off or landing?
METAR and TAF is both true. So there's a difference between the runway, which is magnetic, and the wind direction, which is given in true. So, and when you look at your decoder, it says it in there. Let me just see if I can find the decoder quickly. There we are. So here's the decoder, and so this is the METAR, and it says here winds from, and that's why I highlighted this in yellow, right? It's true, and so this is the METAR, and then the TAF. There's the TAF. Okay, so forecast, wind, surface. Okay, it doesn't say that it's true, but it is also true. But the fun, really surprising thing is that it is true in the METAR. This is basically where you want to find out what runway to land on, right? So it should really be, in my mind, it should really be, yeah, and there's the height, the height, wind at height 270 true, and 50 knots. Okay, so let's go back.
I guess around here where it's only 9 or 10 degrees difference, the runway doesn't make a lot of difference. But
you can ignore
found in 30 degrees could be a whole different runway.
It makes a difference. Yeah. And where I started flying in Germany, I mean, the variation was even lower. It was sort of almost negligent, like 3-4 degrees, right? Wasn't much. Okay, so it is the right answer here is 250 degrees, and it's true. This is one thing you need to remember. Okay, so I guess this is the funny question here. Which would result from a pilot making wise decisions before flight? So all of the above, right? So yes, gotta make wise decisions when you fly. Otherwise, you don't live long. Okay. So which is not an air mass or frontal thunderstorm type? Okay. So when they talk about thunderstorms, it is always convective. It's always with cumulus, right? Keep that in mind. Okay. Um, Orographic. Yeah, that's not all that wrong, but it's okay. Warm frontal. There's usually no thunderstorms in warm fronts, right? Cold frontal, and it says which is not an air mass or frontal. So the frontal thingies, they fall out, right? Then there's advection. That's basically when air flows into an area from a lake or something like this. This is advection. That hasn't doesn't really give you thunderstorms. Rural. This is just thrown in to confuse you. And convection. That's it is every thunderstorm is convective, is created by convection. So even if it's not a frontal thing, you could get on a hot summer day these thunderstorms that all of a sudden disappear on a hot summer day. They are convective thunderstorms, and that's really what. There's no air mass change. There's no front. It's just the convection. Okay, that's the right answer here. Orographic makes clouds but no thunderstorms. This is when the orographic is when the wind blows at a hill and goes up. Okay. Okay, what is the name given to daytime heating thunderstorms? You should all know this now. Noah.
Convection.
Convection, just as I said. Yep, good. Okay. What is the most serious type of precipitation associated with flight and why? Remember? Ray.
It's D, freezing rain.
Freezing rain, yes. Freezing.
You just gone through that a few 10 or 15 minutes ago.
Yep, freezing rain is the worst if you encounter this, and this is so scary if you encounter that. I mean, this is typically power flying thing. You gotta get out of it. You gotta land.
Hail has brought down jets before too, so
Hail is
not a
bad
good one.
too. Yeah, I mean, hail can, depending on how bad it is, it can be baseball size, right? And we have had in there was in Utah at a competition. We had pretty nasty hail. Not good. Okay, but freezing rain is terrible.
There was a DC-9 brought down with hail, with broke cockpit windows and flamed
Yep.
out the engines. And
Oh yeah, hail is, but it's just not any type of hail. It is really big hail, like, and it can be baseball size. Hail has shredded gliders. In the old days, if you wanted to get an altitude diamond, you actually had to climb into a cumulonimbus and ride it all the way up to 7 or 8 thousand meters, right? So 25,000 feet, and some of these gliders were shredded by hail, right? The pilots possibly too. It was pretty crazy, right? Some landed hours later in a parachute somewhere. Some were still alive, but not all of them. So it's pretty bad. We don't do this anymore. We are using Wave now, but this was before Wave was discovered. Okay. How can temperature increase at the surface after a cold front passes? Okay. Um, who wants to take a stab at the answer?
I'm going to guess C.
Yep. That's the right answer. This is the typical, your cold front comes through, and as you know, after cold front, it clears pretty quickly. So at the end of the cold front, when that is through, quite often you get clear skies. And with the cold front, you get cold air in, but then the clear skies settle when the sun comes through, right? And it warms things up pretty quickly. And guess what happens when there's cold air and the sun is strong? You get good thermals. And once the cold air wedge is thick enough to give you 4,000 feet or something like this, then it's good gliding. So typically that happens 24 to not 12 to 18 hours after thunderstorm, after a cold front went through. Okay. Okay, so you can write your own METAR if you like. Okay, we don't do this. As another thing is the air masses in Canada. In Mark McDermott's PowerPoint, look this up just in case there's a question. I don't think there will be questions, but there's 3 or 4 typical air mass, like a dry polar air mass and a wet maritime air mass. And the weather makers here in where we are is always when the northern air mass, the cold polar air mass, dry, collides with the warm and moist air mass that comes up from the maritime air mass from the Gulf of Mexico or the Gulf of America, as they call it now. And so that's, just sort of read over it about what these air masses are called, and look it up in Mark's. Do you all know what I'm talking about when I say the PowerPoint, Mark's PowerPoint? There's a whole course on the PowerPoint, and you can search it by keyboard, right? So you just go to the proper slide. Okay. Okay. Relative humidity is expressed in what units, and dew point is expressed in what units. Okay. We all know that, right? Noah, you know that.
D.
The percentage and in degree C. Yeah, very good. Thank you. Everybody else knew this too, I hope, right? Yeah, I see nodding. Good stuff. That's pretty basic. Okay. Okay. In a TAF, what unit of measurement is used for cloud height? Do we know that? We pick Greg.
Let me think. Above meters, feet. So I think it's in feet above sea level.
Okay, so this is one of those questions where you can narrow things down, right? Because it's altitudes definitely in North America are always expressed in feet, right? So it can only be C and D. So you already have 50% chance to get it right. But it is not above sea level, it is above ground. And why is it above ground? So this is in the TAF. It's the terminal forecast. And when do you need the terminal forecast? You need that when you want to sort of land at this airport. And all the IFR minima, the IFR also has minima, are all related to height, cloud height above ground. At some point, the sea level doesn't really do it for you. You have to, at 200 feet or so above ground, you have to see the runway. And therefore, it gives you all the clouds in above ground. If you go to the area forecast, remember this is the big chart. There, the clouds in there, they are above sea level. And typically, it says there's a cloud, a cloud layer that is from 3,000 to 6,000 or so. This is above sea level. But the TAF and the METAR are both above ground, because that's what you need to compare it to the minima if you make an IFR approach um, on the charts. Okay. Again, it's not something we as glider pilots need, but we need to know, because sometimes, for example, if I'm not so sure if we have enough cloud clearance to do a meaningful training, I have a meaningful training day, I look at the TAFs, right? And if it says 800 feet or so, then there's no point in going out to the airfield. But if it says 2,000 feet, hey, perfect. And it's sometimes difficult to gather anywhere else. The height above the cloud, height above ground. Okay, and then we are back to winds over Toronto at 30,000 feet. And what are they? Okay. So who can read me this? There's a print error in there, a typo. This got to be a 2. Cannot be a 7, because the okay. So let's assume it's a 2.
Well, that'd be 270 degrees,
Yeah.
2 knots,
Mm-hmm.
and the 31 I'm not sure of.
Mm-hmm. Yeah. This is rather strange. Either they have a real typo there, or they report the weather at 30,000 differently. They report it at 24,000. Sorry for that. We'll jump that. Okay. What's the temperature dew point spread at Hamilton, CYHM? So, okay, who can tell me what the temperature dew point spread is? Let's say Brad. Yep, it's 8 degrees from 16. That's the dew point to 24. The temperature is 8 degrees. Okay. Okay, so let's look at our answers there. There it is. 8 degrees Celsius. Yeah, because all these temperatures are in Celsius. Right? In the US, I'm not so. I think in the US they're also Celsius, but I couldn't say 100%. But again, our exam deals with Canada. Okay. Okay, so this now looks at the area chart. How fast and what direction is the low pressure system moving, found on the cloud and weather? This is the graphic area forecast. Okay, well, let's look at, there's the graphic area forecast. By the way, these we haven't really gone in depth into these graphic area forecasts. I showed you an actual one, how to access them, and all the things in there are pretty intuitive. So I don't want to, and also this it's really questionable if there will be a question, right? So we have in this graphic area forecast, we have a high here, right, with 1023. We have a low here at 1002. I should make this bigger so we can see it better. So, okay, here's our low now. Can you all read the 1002? You should. Or is it still too small?
Well, I can read it.
Okay, now you should definitely be able to read it, right? Okay, so here's our low. Okay, and in what direction is it moving? See that arrow there? That shows
Yeah,
you what
like northeast
northeast and at
at
what speed?
15, would that be knots?
Yeah, I'm pretty sure that it's knots. Yeah, so let's look for an answer that says northeast 15 knots. So it's pretty clear, right? And the pressure here was the high, and so this clouds here, so it's patchy, broken layers of stratocumulus clouds, reasonably good visibility from 1500 to 4000, and that would be MSL here. So it gives you the lower and the upper, so above 4000 you're above it, below 1500. So if you need to land somewhere in this area, you have to get through that layer of clouds. Okay, so we go back to okay. So how fast, what direction is the low pressure system moving? Found. So it moves northeast. There's two northeasts in there. So you're down to two options, right? It's 10 knots. No. 15 knots. Yes. C is the right answer. Okay. Okay. What time period would you expect the wind to be 40 knots at CYHM Hamilton Airport? Let's take a look at this. Where is Hamilton? I can zoom out of this a little bit again.
Yeah, it's just above the taps there. There you go.
And
Oh,
there we are.
That's
Okay.
the taps. Yeah.
That's the TAF. That's the TAF. Yeah. Okay. This is the Hamilton TAF. So the question was. What time would you expect the wind to be 40 knots? Okay, let's look for 40 knots winds. Okay, so here's the TAF. Okay. None in here. And this is a probability 40% here between 2300, 2100 and 2300. And there's gusts 40. Okay. That's just the gusts 40. And there's 3 miles thunderstorm. TS is thunderstorms, right? Then in rain showers. CB, so broken at 3000, the CB, that's a cumulonimbus. It's bad, bad, bad. Okay. So it is between 23 and 21 and 2300. Okay, and is this the next day? No, it's not the next day yet. Okay, let's see what the answer options are. Hey, there it is. So it's at 2100. No, it's between 21 and 23, and it's not after 23, and it's not before 21. Okay, pretty easy, right? So you may get a question, a TAF, and then a few questions like this as well, and it's fairly easy to do. So don't give away any points on that one. Okay. Any other questions on that? I gotta look up my notes. Oh yeah, we wanted to do something else. So we'll, if you want, you can go a little further in these questions and see what you can answer. The list of questions that I think you should be able to answer is in my email I sent to you. But I want to take the rest of the time to do something else with you, so we can close these. And yes, so I did an analysis from your homework. Thank you very much for all the people who did homework, and thanks Noah for putting yours in. So this is all, this is from the GS1, 1 to 50. And each column here represents one of you, the answers you gave, and everything that's red is an incorrect answer. So if I go through there, I see question 29, we had out of how much do we have? 7. We had out of 7, we had 5 incorrect answers, right? And they all did the 1, right? So we should revisit this question. And then we had a few with 3 incorrect answers. There's another one with 4, and so let's bring this up and have a look. Okay, the GS1. Okay, can you read it? Make it a little bigger. Okay, I think you should be able to read it, right? Okay, so the first question we want to go at is this here, 4 wrong, question number 9. Okay, when 2 forces are equal and opposite, as well as parallel, but do not pass through the same point, they are said to be a parallelogram, a triangle, a couple, or a pair. And a lot of people got that wrong. And everybody, well, the majority said 1, right? So majority said a parallelogram. No, it is a couple. And I'll show you I think I sent out the picture a lot. I'll show you, put the picture up here. So this is your typical tighten up your wheel nuts type of thing. So you're pushing with one on one side down, we are pulling on the other side up. It's equal forces. Otherwise, that thing wouldn't stay where it is, right? And it doubles the torque that goes in there, basically. So you have the torque, basically this force times this arm, and this force times this arm, and they both turn in the same direction. So this pair of forces is called a couple. Just in case you get something like this, right? So and it is forces that are parallel but opposite, and they don't cross each other, or what's there something else when 2 forces are equal and opposite as well as parallel. So they're equal and opposite and parallel. That's the criteria for a couple. Okay, so keep that in mind in case you get that question. Can you all see the picture? Here we go. So equal forces but opposite. These are basically represented by the red arrows, and they're parallel. Couple. Here it says. Okay. So that's one of those questions. Okay, so this was this guy. Then the next one, there's 3 wrong, 19. Let's go to 19. Okay, let's see what people did. A lot of 3s in there, when the right answer was 4. Okay. Lateral stability is aided by having. Do we know what lateral stability is? This is the roll stability, right? It's not a stability around the lateral axis. This would be the pitch, the roll stability. So what helps us with roll stability? It's dihedral, like this. And if the CG of the airplane is further below the wing, that helps too, because it's like a pendulum, right? Okay, let's see what it says. Okay, 19 is aided by center of gravity lower than the center of pressure. Yes, it's true, but you have to read on, right? Then number 2, a large angle of incidence on the wings. No, it's wrong. That's there to confuse you. Do you know what the angle of incidence is? That is the angle between the fuselage and the wing. And it is not the dihedral. It is basically, I should find a picture. That's hard to explain without a picture. Basically, how much angle of attack the wings have versus the fuselage. So it's the angle of there's the chord, the wing chord goes from trailing edge to leading edge, or vice versa, right? And that angle between that chord and the angle, the longitudinal line in the fuselage, that is the angle of incidence. Okay, and that's basically baked into the airplane. Okay, so that's not so. This is not right. Then having a dihedral angle on the wings, that is right. But this is also right. But since 1 and 3 are right, number 4 is the right answer. So yes, all the people who said 3, they were correct, but only half correct. So you have to read the whole thing through and make sure, because you don't get any points if you only have it half correct. This is, in the end, still wrong. You don't get half points for that. Okay, so this is one of those tricks with these questions, right? Read all the answers through, and quite sometimes there is basically this and this and this is correct, and this could be it, right? So in that case, it is. Okay. Then here we go with the one five wrong and all the same, right? 29. Let's see what 29 is all about.
Can we go over 20 as well?
Sure. 20, yeah, 3 wrong. Okay, let's go 20. Sorry. Okay. Where is 20? Okay. As the angle of attack of an aircraft increases, the center of pressure moves forward, or the center of gravity moves forward. Do we know what the center of gravity is? This is where all the weights in the airplane are concentrated, right? And that doesn't move as we move the angle of attack, right? This is basically the way you loaded the airplane sets the center of gravity. Doesn't change. Okay, so that's definitely not the right answer. Then the drag increase. Okay, where are we? 20. The angle of attack of an aircraft increases. The center of pressure moves forward. The drag increases and the lift increases. This is correct. The drag increases and the lift decreases. This is wrong. So the drag, no, this is drag increases, lift decreases is wrong. Drag decreases and lift increases is wrong. Basically, drag and lift would increase. So both 3 and 4 is wrong. Number 2 is wrong, has nothing to do with it. So number 1, the center of pressure moves forward. But there is, and I have a picture to this, and this is in the, let me see, yep, this is the picture. Because there's another question to that. Okay, so here's our CG that doesn't move. This here is the angle of attack. This is the angle between the airflow and the chord line. So now we increase the angle of attack, and the lift increases, of course, right? And the center of pressure moves forward because the lift increase is stronger near the nose. That's why the center of pressure moves forward. And I'm going to go back to the question here quickly. Increases, the center of pressure moves forward. That's why number one is correct. But I have to go back to that. There's another question that says, what happens to the center of pressure when you stall? And when you stall, the right answer is the center of pressure moves back. And of course, people say, well, first, when the angle of attack increases, it moves forward. And when I stall, it moves back. This is what's right now, right? Because you stall, if you increase it further, then you stall. And what happens here is the following. So here the wing is now stalled, right? Before that, when the center of pressure was up here. So when you stall, the lift up top, over top of the wing basically collapses because the airflow separates from here on and doesn't follow the airfoil anymore. And that means the only lift you're getting on that wing is from the downside because you're going through the air like this. And the center of pressure is basically moving back to where it was initially before the angle of attack increases. So it's before you stall, it's up here, and then it snaps back to here, which is a good thing because it helps you to bring the nose down. So be careful what is being asked. Is the question what happens in a stall? Then the center of pressure moves back. What happens when the angle of attack increases? The center of pressure moves forward from this position. Okay, that's why I pull this out. Good question, Noah. So this is the question 20.
Can I just ask a question there? So if you increase the angle of attack, you're going to stall eventually. Won't drag increase and lift decrease?
If you increase, when you stall, then what happens is that the drag increases and the lift decreases, but
Yeah.
only after the stall, not when you just increase the angle of attack. That means you're still flying, you haven't stalled yet. And so initially, as you increase the angle of attack, the lift increases and the drag increases. And so neither of those 3 and 4 are correct. But of course, once you stall, then the drag keeps going up further and the lift decreases, it collapses. Okay, so that was 20, and on 20, so 1 is the correct answer, and we had a mix of other answers. Okay, so now let's go to 29. 29. Thanks, Noah. That was good to revisit that one. Okay, what would the effect on an airspeed indicator during a climb be? What would be the effect on an airspeed indicator during a climb if the pitot line were completely blocked? This is the pitot question, right? And all the people who said 1, they're very correct. It ceases functioning, but it's not the correct answer. Unfortunately, I mean, for all practical purposes, the airspeed indicator is wrong. It's not giving you any sensible information. But the technically correct answer, and is a useless answer also, is that the airspeed indicator would now behave like an altimeter. And why would it behave like an altimeter? Because you have air stuck sort of in the pitot line still, and it's totally blocked. And you're climbing, so the surrounding pressure decreases, and you're getting a differential between what's in the pitot line and what the surrounding pressure is. So the airspeed indicator starts going up, and it's basically the higher you go, the more it goes up. It works like an altimeter, but the heinous thing about this is that it works like an altimeter is basically useless information. What you need to know is it will give you an erratic speed reading, and airliners have crashed because of that. There's a, and I think I sent that YouTube out. It's a Mentor pilot YouTube where this happened. They had a blocked pitot line, and as they were climbing, the airspeed got higher and showed higher and higher and higher, and they slowed down and stalled the airplane and crashed the airplane, and 100 people died. So this is basically the airspeed indicator is useless. That's true, and it is actually giving you, if you follow it, it makes you stall your airplane. Now, as glider pilots, we can see when we stall and we can feel when we stall. So it's probably you probably figure out the airspeed indicator is just not working. But if you see something like this, if you if you start taking off and the airspeed when you lift off still says 0, then there is something wrong. There's probably a pitot, and then as you climb, it'll actually start going up. And the mistake would be to think, oh, now it's working. No, it's going up because the outside pressure is dropping, and it's giving you an erroneous reading. Don't believe it. If it's not showing anything as you take off, just disregard the airspeed indicator. You can fly without it, right? You don't need an airspeed indicator. But what's really dangerous if you try to follow what it says, because it will tell you to slow down. And that's not something you want to do to the point where you stall, right? So, but for this type of question here, and is the airspeed indicator would behave like an altimeter, because that's what it does. But it is, so it's correct, but useless, the answer. And all the people who said it ceases functioning, in my mind, all the ones here, you all were right, but the 4 is the right answer. Sorry for that. Okay. So just keep this in mind. If that question comes up, it is not, the right answer is not the ones that make sense or makes any sense really, or gives you any sensible information, because you can do nothing with that it works like an altimeter, but you have an altimeter. You don't need your airspeed indicator to read the altitude, and it always shows on the airspeed, right? You can't even connect this to altitude, but it will function. The needle will go up as you go higher. Okay, so that was the 29, and then 30. We have also 5 wrong. If a pilot does not apply forward or backward pressure to the control stick to keep a constant flying attitude, the aircraft is said to be in what? And I think most people said equilibrium. We have 3 said equilibrium, and 2 said and 2 said lateral trim. Be careful, lateral trim is roll trim, right? It's not a trim around the lateral axis, right? This is pitch trim, and so the simple answer is the airplane is in longitudinal trim. So as you fly along, and that's what your trim lever does. It's longitudinal trim. It basically sets where your nose goes, right? And so if the stick stays there and it's flying a constant speed and doesn't do anything else, it is well trimmed, and it's trimmed to that speed. That's what it says. Okay. We're past 9, but let's quickly do 31 and 42, and then we go home. Okay, the lift force on an aircraft in flight is considered to act. Okay, which way does the lift act? By definition, lift is always perpendicular to the airflow. So 90 degrees to the airflow. That's the definition of lift. Okay, and so we go. What are the answers? Upward with reference to the Earth through the Sea of G. No. Upward at a 90-degree angle to the wing chord. No, this has nothing to do with the wing chord. At right angles to the airflow through the center of pressure. That's what it does. So it's number 3 is the right answer. And we have one answer is 1, upward with the reference to the, well, yeah, it's not totally wrong, but it's still the wrong answer. And then we have a 2, upward at 90-degree angle to the wing chord. Well, the 90-degree angle is right, but it's to the airflow, not to the wing chord. And then we had a 4 at an angle to the stalling angle of the aircraft. There is no such thing as a stalling angle of the aircraft. Okay, so that was the 31 and the last one, 42. Okay. Ooh, this is a right-away question. You shouldn't get those wrong, right? When two aircraft are converging on converging courses at about the same altitude, that's the question, which aircraft should give way? Do we know the rules? It's always the airplane you see on your right. It's just like on the road. The airplane you see on your right has the right of way. So it's right over left. And at night, they have position lights, right? And so if you see a red light, which is the right on the left side of the other airplane, that means give way. He sees your green light on the right side, and so he knows he has the right of way. Okay, so let's see what the answers are. The aircraft with the other on its right shall give way. Yep, that's the answer. Number 1. What's the next? The aircraft with the other on its left shall give way. No, it's right over left. Both aircraft shall turn to the right. No, that's when two airplanes meet head on. Then both should turn to the right. Okay. And both aircraft shall turn to the left. No, that's totally wrong. Okay. So that's pretty easy to understand, and this is something of all the many questions you have here. That's something you need to know for actual flying. So it's the airplane you see on the right has the right of way, but don't push it. Both pilots have the responsibility to avoid a collision. You can't just say, "Well, I had the right of way," and plow through the other guy. But it's the airplane from the right has the right of way if it's the same type of airplane. Now, if it's a glider that has the right of way over everything else except right.
A balloon.
Balloon, yes, that's right. So the gliders are, so there's two types of questions. There's either the same type of airplanes meet somehow, that you need to know who has to give way, or different types of airplanes meet, then it's pretty clear. If it's a glider, it has the right of way over everything but a balloon. Okay, with that, I wish you
One quick question is,
yeah,
so if the plane on the right is a powered plane,
yeah.
you have priority still.
If you're a glider, you have priority.
So the plane has to get out of your way.
Theoretically,
Theoretically,
has to give way. Now, in reality, these are Cessnas. They're now all flying with iPads and so, and they're all looking at their iPads and they're not looking out. We see this with these Cessnas from the flight schools that fly around in our area all the time. They are never looking out. and so you better avoid them, right? You can see them much earlier and easier than they can see you because you don't have struts in the way and wings and all that kind of stuff. You have clear vision, right? And when you see these guys coming, if it doesn't move, if there's no angle change, right, then you're on a collision course. If it moves, if the angle moves, like if it moves on your canopy, forward or backward, that's okay. Then you're not going to hit it. But if it's a constant bearing, with boats the same, right? Then you're on a collision course. So then they both come together like this, and boom. Okay, well, one more to come next week, and then off you go. And I'll find out if we need letters of recommendation. And but what I have always sent out in the past for all of you is a certificate that says you attended so and so many hours of ground school. And if you attended all of them, it's 10 hours. It's 20 hours, sorry. And 15 is the minimum. And you also, if you attended the spring course in spring there, the basic ground school, that counts as well. So, but normally this here gives you enough hours, so we don't have to worry about the other one. Okay.
Thank you for everything.
Hey, you're welcome. So far, we've had 100% rate, so in people passing. So please continue that.
It's too much pressure.
Yeah, and I'll send you a little bit of homework again, and also another riddle, so like the Magellan riddle, the follow-on riddle. So now you're in this riddle. You will be the first officer on a flight to Japan, on an Air Canada flight to Japan from Vancouver. And you have to make a decision and see if you make the right decision. Okay. Have a good night.
Thank you.
Good night. Thank
Thank
you.
you, York.
Good night.
Thanks, Eric.
Good night.